So I'm here, you're hopefully familiar with ALTIUS by this point. I'm just going to talk about, at a high level, what my colleague Nick Lloyd and I have done for the in-flight calibration for ALTIUS. So there's 3 channels that we need to calibrate for. There's the UV, the vis, and near-infrared imagers. And there's no onboard calibrations lamps or diffusing spheres, so we're going to have to rely on natural targets such as the sun, moon, atmosphere, ground targets, and so on. And there's 5 main products that we'll be putting out, which is the photo response non-uniformity, or PRNU, the absolute radiometric calibration, the spectral response function, or SRF, and wavelength registration, the point spread function, or PSF, including the core and the stray light tails, and the polarization response. And this is going to help us characterize the transmissions from the front end to the back end detector. So for the PRNU, normally when we calibrate, you'd assume you'd have a uniform source at the front end and look at the variation you see across the detector. In space, we don't have any source that's going to extend across 2 degrees field of view, so we have to do our best to mimic that. And in doing our best source we thought we could use is the sun, where we can scan it across. And I've shown here the PRNU that we see due to the AOTF and the telecentric optics that produce this sort of pattern at 450 nanometers. So if we scan the sun across, we can mimic this uniform source, and hopefully this underlying PRNU is revealed. And since we have about a 2 degree field of view, the sun's half a degree, and we're going to use about the innermost portion of it, we need at minimum 64 images to fill our field of view. So obviously the sun isn't perfectly uniform. I've simulated an image that we might, image of the sun here, and you can see the underlying PRNU pattern, but we also get the solar limb darkening. And so that itself has to be removed before we can use it as a uniform source. And luckily that's fairly well modeled by, was it Pearson Slaughter, I think we were using for our model in the top right. So it's just it's quite sensitive to how well we can center the sun. So I've sort of tried to depict that in that bottom right picture. If we're off by even a few pixels in our centering, we can produce an artificial gradient. So we got to watch out for that. And there's other things that we got to worry about, like the granulation, which in our simulations it didn't introduce enough noise to be of major concern. It was more driven by shot noise. And right now, for handling sunspots, we're just going to flag them out and ignore those pixels. So once you gather once you gather images and remove the limb darkening and stitch them all together, you obtain a calibrated PRNU map on the bottom left. And I've just shown the relative difference between that one and the true PRNU. And I've just flagged pixels that were above 1% in red. And the histogram just shows that we're getting about a 0.6 plus or minus 0.6% difference, which is within the 1% requirement. And then we can move on to the absolute radiometric calibration. So that's just our conversion from detector electrons to units of radiance. And for that, we'll just use the SAO 2010 solar spectrum as a reference. And we'll just obtain a modeled image of the sun that integrates to that total irradiance and divide it by the PRNU corrected image to obtain a ABSCAL. So moving on to the PSF, if we have a point source of light, we'll see some sort of angular spread on the detector, and that can be divided into 2 main regions. One is in very narrow angles, we're calling the core, and beyond, on further angles, we have the stray light or tails. So we have to do those in 2 separate parts. The first part of this calibration is to do with the core. So for this, we're using sort of a knife edge technique where we're just going to look at the edge of the moon and how the signal drops off. And for the data we are working with, the core is generally Gaussian shaped, so we ran with all our simulations assuming a symmetrical Gaussian shape for the core. And here is just a simulated image of the moon with the PSF convolved to produce that blurred edge that you'll see. So when we take slices across the moon, we map those pixels to radius of the center of the moon and aggregate all of them into a single edge spread function so that we can obtain high resolution subpixel sampling of that edge, which I've shown here. And you take the derivative, you end up with the line spread function. And under the symmetric 1D assumption of the PSF, the line spread function gives a very close representation of the point spread function. So it's simply just fit a Gaussian to this and obtain an estimate of the width of the PSF core, which I've shown on the right. And I've compared it against the actual PSF, which has also a tail component. Obviously, for the edge analysis, we don't get enough signal to analyze the tail portion, so we end up slightly overestimating the width due to that additional blurring, but it's on the order of 2 or 3%. So for the tail or stray light calibration, we can't really image anything on the detector because we're going to saturate and even start blooming before any signal for the tail appears. So we have to place the moon outside the detector field of view. And I've sort of shown that with this little animation here, how the signal drops off. And here's that's just a example of the PSF. We have the very narrow core and then a much slower drop off of the stray light. And there's two main components, the near field and the far field, and both are modeled by scattering processes governed by the modified Harvey function. So we assume a modified Harvey fit for all our simulations. And for the tail calibration, we obtain a measurement with the moon outside the field of view. And we also have to grab an image of the moon on the detector, and then for our simulations, we're going to place that outside the field of view, convolve it to perform a forward convolution with a 1D modified Harvey PSF, and iterate on those parameters until we get an agreement with the measurement. And in doing so, we obtain a fit to just a small slice of the PSF, and which only represents a small portion of the full 2D PSF, and we're going to have to take the images at several different angles in order to reconstruct the full 2D. Moving on to the SRF, our strategy is simply to scan Fraunhofer features by looking at the sun. We were looking at the sun quite a bit for these calibrations, so we'll use the standard stretch and fit algorithm for that. There's an added complication with the UV because we have that stack of 4 Fabry Pros. We have to do it in 2 stages, and we're limited to actually only a handful of wavelengths as opposed to the whole spectrum. So we have to apply the fit that we obtain for those few wavelengths to the whole spectrum. And in the vis and near infrared, we have much simpler AOTF, which just generally follows a sinc squared shape, so we can just do a standard scan across lines. And we had no problems with this. We just we want to verify it with the vendor data because we had to work with idealized SRF shapes for this one. I'm going fast. Lastly, the polarization. In order to make an estimate of the polarizer Mueller components, we're going to utilize something that was done on OSIRIS and a few other missions, where we pick a line of sight that is completely out of the sunlit portion of the atmosphere, where the tangent point's at 60 kilometers altitude and the solar zenith angle's at 94.5 degrees. And this puts it well above ozone and aerosol contributors, and virtually no ground signal comes from this. So as doing so, we can obtain this geometry in the bottom left, where we obtain Rayleigh scattering polarized signal. As we keep looking at the same point, we can sample it at different different polarizations. And that just follows the satellite maneuver, where the green is the satellite motion and the blue is the tangent point, where we're constantly rotating to see that same special point. And the top right is just the simulated front end radiance for each polarized component. And then using our radiative transfer model, that's obtained using SASTRAN. And when we apply a linear polarizer on top, we can simulate a signal, and we are quite easily able to fit to this. So don't see any problems here. So not much for conclusions. This is still fairly preliminary work, but we're integrating the calibration software into the system performance simulator currently, and just awaiting a few more the latest data for certain components just to verify our techniques. And in most cases, we meet the system requirements. So that's all I have. Thank you for your time.